Hello, good evening. This is a problem solving session uh, basically for the week 3 content. This session address some of the sample problems from week 3 content. So basically, if you look at the content of week 3 and week 4, these are the topics of discussion. First is AC signals in lossless transmission lines. So we look at we already looked at lossless transmission lines and with a DC source. So this week 3 lecture start with a discussion on when these transmission lines have an input AC source, and a discussion on the reflection coefficient and also the input impedance. So to give a brief of what was covered, so the solution of wave equation looks like V of z is equal to V plus e raised to minus j beta z plus V minus e power j beta z, wherein this term is the forward wave and the second term is the backward wave. This is a solution of wave equation. Here if you write it in terms of time domain form, we can write this as real part of modulus of V plus e power minus j beta z e raised to j omega t. So in this lecture 7, there is discussion on several conditions of the load. Say if the load is open circuit, or I can say ZL is infinity, and also when ZL equal to 0, that is when the load is short circuit. So under these two conditions, there are discussions. So to brief out those discussions, whenever there is an open circuit connected at the load end, the reflection coefficient gamma L is 1, and the voltage equation reduces to be V naught plus into e raised to minus j beta z plus e raised to j beta z. So it becomes 2 V naught plus cos beta z. This indicates that the maximum voltage on the transmission line will be 2 V naught plus. Now there is also discussion on input impedance. So let us have a look at Zin. So the general expression for Zin is Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. So whenever ZL is infinity, this reduces to Zin equal to minus JZ0 cot beta L, and whenever ZL equal to 0, this reduces to Zin equal to JZ0 tan beta L. So these two relations are very important. This will be helpful in solving the sample problems. So moving on, the next lecture, that is lecture 8, deals with transmission lines with losses. To give a brief of what is transmission line with losses, we know that whenever there is a lossless transmission line, we have R and G as 0. But when there is losses, there is a finite value for R and G, that is resistance and the conductance. So the eighth lecture deals with the transmission line equation, solution of transmission lines when there are losses. So in case of a transmission line with losses, the solution of wave equation becomes V of z is equal to V plus e raised to minus gamma z plus V minus e raised to gamma z, where this is the forward wave and this is the backward wave. Here the parameter gamma, which is called as the propagation constant, is defined as alpha plus j beta, where alpha is the attenuation constant and beta is the phase constant. Now, say if you take the forward wave into account, V plus e raised to minus gamma z. So instead of gamma, if I substitute alpha plus j beta into z, so this becomes V plus e raised to minus alpha z e raised to minus j beta z. So if you look at this equation, this is a term which indicates there is an exponential decay for a wave traveling in the plus z direction, in this case which is a forward wave. So there is an exponential decay for a wave traveling in the positive z direction. So if you have a plot of this looks like this. So there is an exponential decay for the amplitude with the uh, direction in the direction in the with the position. So in case of a lossless transmission line, we know that alpha is 0 in case of a lossless line. There is no attenuation, there is no decay on the amplitude of the wave. Whereas if there is a lossy transmission line, there is an attenuation for the wave which will account for this exponential decay in the amplitude of the wave. So let us move on to some sample questions. So let us discuss the first question, that is a 300 ohm lossless transmission line of 0.8 meters is terminated with a short circuit. So here let us note down the things. Z0 is 300 ohm. Then the line length is 0.8 meters and it is terminated with a short circuit, which indicates that the load is ZL equal to 0, and the line is operating in air with the input voltage of 10 volt and wavelength of 0.3. So it indicates that the input voltage of 10 volts, so the maximum voltage or the amplitude of that is 10, and the wavelength lambda is zero point 0.3 meters. Now the question is, we clearly know that the load is short circuited, so what will be reflection coefficient will be minus 1. Now we also know what will be the maximum voltage at any point on the line. So as we discussed here a few minutes back, so the maximum voltage, say if gamma L is equal to minus 1, so the maximum voltage can be written as V plus into 1 plus mod gamma L. So V plus into 1 plus modulus of minus 1, so that will be 2V plus. So we know that V plus is 10, so the maximum voltage will be 20 volt. Now to go to the second part of this question. To go to the second part, the current amplitude in this short circuit. So what will be the current here? That will be I max is equal to V max by what is the impedance? That is Z naught. So 20 by 300, which is equal to 66.6 milliampere. So let's move to another question. A load of 100 plus J150 is connected to a 75 ohm lossless line of length 0.6 lambda. So let us note down what is available in the question. Load value is 100 plus J150. Z naught is 75 ohms, and we also know that it is a lossless line, and the length of that line is 0.6 lambda. Now let's see how to calculate each of these. First question is the reflection coefficient. So let's see that the impedance, load impedance is complex. So because the load impedance is complex, the reflection coefficient will be calculated as ZL minus Z0 by ZL plus Z0. So 100 plus J150 minus Z0 is 75 divided by 100 plus J150 plus 75. So this will be simplified to be 25 plus J150 divided by 175 plus J150. So if you take the division, we get it as 0.66 angle 39.9 degrees. So this is the reflection coefficient. So reflection coefficient is complex, which has a magnitude and a phase, which is clear from the complex value of this.
Hello. Yeah. Mm.
Now next is the calculation of VSWR. So to calculate VSWR, VSWR is equal to 1 plus mod gamma divided by 1 minus mod gamma. Okay. So here mod gamma or modulus or the magnitude of gamma is 0.66. So 1 plus 0.66 divided by 1 minus 0.66, which will be 4.88. So this is the voltage standing wave ratio. Now to go to the next question, the location of first Vmax with respect to the load. So to talk about the location of Vmax, so we know that we have a Vmax when phi is even multiples of 2 pi by lambda, Okay, so here the phase of the reflection coefficient angle gamma is 39.9 degree, could be approximated as 40 degree. So let me write this 40 degree. Okay, let me write gamma as gamma L e raised to j. Instead of 40, let's make 40 into pi by 180. 40 into pi by 180. So this comes out to be 0.698 radian. So 40 degree is 0.698 radian. So when we write, this will be e raised to j5. So let us write like 0.66 e raised to j. So instead of 40, we have to write it like 0.698. So it has to be in radian. Now we know the phase, that is 0.698. So the location of first Vmax is this phase divided by 4 pi into lambda. So first Vmax position will be 5 by 4 pi into lambda. So 0.698 divided by 4 pi, and lambda is in the question, that is 0.6 lambda. So sorry, lambda, sorry, here lambda has to be, okay, we can just write it as lambda. So 0.698 by 4 pi will give me 0.055 lambda. So the location of first Vmax will be 0.055 lambda. Okay, so it's in, the location is in terms.
Next question is the location of V minimum with respect to the load. So when I say V minimum, say we all know that the standing wave looks like this. So this will, if this is the V max, so this is the V min. So it's very clear that the distance between Vmax and Vmin, or the distance or the location difference between Vmax and V minimum, will be lambda by 4. So if you have the first Vmax, so the position of first Vmax plus lambda by 4 will give us the position of first V minimum. So first Vmax is at 0.055 lambda. So it will be 0.055 lambda plus we have lambda by 4. So it will be 0.25 lambda. So the answer, I mean the position of the first V minimum is 0.305 lambda. Okay. So this is the answer for the next part. Okay. Now let's see the last part of this question. Zin at the generator. So that is the input impedance. The question is on input impedance. We know the load impedance, we know the characteristic impedance, and also the length. So will you be able to calculate the input impedance? So how do we do that? To calculate the input impedance, we have the equation Zin is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. So this is the input impedance. Now here we know Z0 value and we also know ZL value. Now how about beta L? So let's look at what is beta L. Beta L is the electrical length. So beta is 2 pi by lambda into L. So 2 pi by lambda into length of this transmission line, as per the question it is 0.6 lambda. So this comes out to be 2 into 0.6, 1.2 pi, or in degree if I write it is 216 degree. So let us substitute the values in this equation. We know the characteristic impedance is 75. So 75 into load value is 100 plus j 150 plus j 75 tan of 216 degree divided by 75 plus j 100 plus j 150 tan of 260. Okay. So this we need to simplify. So once if you do this, 75 into 100 plus j 204.5 divided by minus 34 plus 72.65 j, which turns out to be 134.25 minus 165.75 j ohm. So this is the input impedance. Moving on to the next question. Match the following normalized impedances to the points A, B, C and D and E on the Smith chart shown in figure 1. So let's look at each of these points. So 0 plus J0. So this is a question on Smith chart. So you already know the basics of Smith chart from the lecture 11, I think. So lecture 11, you have you are already gone through the basics of Smith chart, that is the resistance and reactance circles, that is R and X circles, and then you have come across the impedance and the admittance charts. So to discuss that, so gamma, if you see in Smith chart, you have circles like this and also circles like this, where you have seen these are R circles and these are X circles, and you also know the upper portion is inductive reactance and lower half of the Smith chart is representing the capacitive reactance. Now let's see the question and analyze all the points. So what is 0 plus J0? So where is this located at? So 0 plus J0, that is R is 0 and also X is 0. So where is this located at in Smith chart, in the Smith chart? So R and X is 0. So basically it is, so we know that Z is R plus JX. So basically R and X both are 0. So Z equal to 0, or I can say it is a short circuit. Okay. So where is the short circuit point? So see the point D. All of us know that at point D, this is R equal to 0 and X is equal to 0, or we call it as a short circuit point. Now, how about the second? B. B is 1 plus J0. So r equal to 1 and x equal to 0. So where is the r equal to 1 circle passing through? R equal to 1 circle will be passing through the center, but x is 0. So x is 0 and r is equal to 1. That is at the center, which is point A here. So this is r equal to 1 and x equal to 0. So point A, so this is A and the first one is D. So D, we call it as a short circuit point, and second B is this point we call it as a matched point. Why we call it as matched point? Because r is 1 and x is 0. Now going on to C. What is C? 0 minus j1. So that means r is 0, x is minus 1. Okay. This is the point. X is minus 1. So lower half of the Smith chart represents minus x. That is the capacitive reactance. Okay. So this is r is 0, x is minus 1. And so this I can write it as, E. Now what about this point? So this will be r is 0 plus x is 1. Okay. So this is representing C. So this represents a inductive reactance and this represents a capacitive reactance. Now what about this infinity plus j infinity point? Where this would be? Look at this point. Here r is infinity, x is infinity, or we call it as an open circuit point. So this will be B. Now moving on to F. Where is F located at? Zin by Z0 minimum. That is minimum input impedance. So minimum input impedance is at the position D. Minimum input impedance. And where is maximum input impedance? That will be at the position B. Okay. Now let's move on to the next question. So this question is on the last 12th lecture, which deals with the impedance matching, that is using an LC matching circuit. So you have come across the video lectures where you have seen using inductance and capacitance how a matched network is formed, basically to match the load impedance to the characteristic impedance of the transmission line. So before going into this question, so this question will give you an overall idea of LC matching network. But to start with, we need to always remember it could be either LC like this, or it could be C and then L like this. So here I can say, so this would be connected to the load and this will be the transmission line, and here you will have the input and all that. Okay. So this Z0 has to be matched to ZL with the help of this LC network. Okay. Or it could be CL. Okay. So here you have a parallel capacitor and a series inductor. Here you have a parallel inductor and a series capacitance. So we need to understand what each means. Okay. So let's try to understand each of them. In figure, so this question will help to understand this. In figure 2, point P. So point P is a normalized load impedance point. Say we have a, say for example, a load ZL. So what do we do? This ZL will be divided by Z0 to get the normalized load impedance. Okay. So ZL is ZL by Z0. So once we get the normalized impedance, we try to plot it on the Smith chart. So such a point is point P. Now this is to, once if you add a LC matching network, so this point P will move. Okay, so where this move is a question. Hello. Hello, good evening. Am I audible?
Hello.
Hello, am I audible?
Yes, ma'am.
Okay, thank you.
Ma'am, this is the doubt clearance section, right? I am joining in the first time.
Okay.
So this is fourth week as in section, ma'am, right?
Yeah, so this is fourth week.
Okay.
And we have we today I think I started I was in the live session from 5 p.m. But
Mm-hmm.
not anybody, no, nobody has joined the session. So I was trying to record the session, uh,
Mm-hmm.
and this recording will be available for all of you to have a look at. So if you are,
Ma'am, ma'am, recording section is available from where, ma'am? In NPTEL.
in the NPTEL site, where you have the course page,
Okay.
you have an Excel sheet link. So
Mm-hmm.
this will be linked to that. So whatever recordings we have will be
Mm-hmm.
uploaded in the same Excel sheet every week.
Last week I find, but I didn't get. I got only 2 weeks recording only.
Yeah, yeah.
Actually, I found for
We have conducted only for 2 weeks. Basically, it is week three. Uh,
uh,
so today is tutorial session three.
yeah,
Okay.
it will be in the right, ma'am?
Yeah, yeah. It will be available in the Excel sheet. So Excel sheet link you will get in the course page.
Okay, ma'am. Thank you.
Okay. So anyway, I'm taking the session as a video. I mean, with a Google Meet on. So if you have any doubts, you can ask me, interrupt me, and ask me. So I'll carry on with my session. Huh? Okay.
Okay, ma'am. Okay, thank you.
So this question is based on impedance matching uh, from Smith chart. So as you have already seen the video lectures on Smith chart, you try to plot a load impedance. How do you try to plot a load impedance? Say if any impedance is given to you, you do a normalization first. Say so if you are given with load 100 plus J50, and the characteristic impedance is 50. So you evaluate the normalized impedance as 100 plus J50 by 50.
1. So if you have a normalized impedance, okay, so let's move on to this question. So adding a series inductor will move point P2. So series inductor, so we know that it's an inductor, and as I already discussed, the upper half of Smith chart represents inductive reactance and the lower half represents capacitive reactance. And adding a inductor, that in series. So if you add an inductor in series, so series and parallel, there are two options. Either you can add in series or you can add in parallel. So whenever you add a reactance in series, it's moving along constant R circle, and if it is in parallel, you will move along constant G circle. So if you look at the R circles here, so these are the R circles. Okay, these are the R circles. So here from point P, if you add an inductor in series, so you will be moving in the along the R circle, that is constant R circle, towards the upper half. Because an inductor is added, you will move towards the upper half of the Smith chart, that is towards point B. So the answer to the first will be adding a series inductor will move point P to point B along a constant R circle and towards the upper half of the Smith chart because an inductor is added. Okay, now let's look at the B part. Adding a series capacitor. So adding a series capacitor will move point P2. So series capacitor. So how do we add series capacitor? So capacitor is basically capacitive reactance is the lower half of the Smith chart. So series will be moving along the constant R circle. So adding a series capacitor, move along constant R circle towards the lower half of the Smith chart. So P will move towards D. Okay. Now coming to C part, adding a parallel inductor. So when I say parallel, we need to understand we have to move along the constant G circle. So G circles will be like this. So it will move towards inductor. If it is an inductor and it is parallel, so move along the constant G circle towards the upper half of the Smith chart. So this will be A. and move again. The last option is option D, adding a parallel capacitor. So move along constant G circle, because its capacitor to move towards the lower half. So it is point C. Moving on to the next question. A communication circuit consists of two lossless transmission lines T1 and T2 as shown in figure 3. Plot in the figure shows the magnitude of reflection coefficient at the input end as a function of frequency f. The phase velocity of the signal in the transmission line is 2 into 10 power 8 meter per second. The minimum length L of the transmission line T2. So this is transmission line T2 and this is transmission line T1. So we see that this is an open circuit connected at the load end, and maybe I can denote it better. So this is Zi1 and Zi2. So for a line terminated in open circuit, I can write it like Zi2. Okay, whenever I write the input impedance of this line which is terminated in open circuit, this Zi2 will be minus JZ0 cot beta L. Okay, so where L is the length of this transmission line, so let us denote it by capital L. It is given as capital L. And what is Z0 of this line? That is 50. So minus J50 cot beta L. So this entire transmission line terminated in open circuit can be replaced by this impedance minus J50 cot beta L. And now that is coming in parallel with 50 ohm. Okay, so Zi1, okay, Zi1 is the input impedance looking at in this direction. So it will be 50 ohm parallel with Zi2. So 50 ohm parallel with Zi2 will be 50 parallel with minus J50 cot beta L. So the input reflection coefficient gamma is ZL minus Z0 by ZL plus Z0. So this graph is for the reflection coefficient, and you see that at some points reflection coefficient goes to 0. So when will this goes to 0? When will the reflection coefficient be 0? Whenever ZL equal to Z0. So this input reflection coefficient becomes 0 when this load, that is Zi1, whenever Zi1 becomes equal to Z0. Okay, so Zi1 becomes equal to Z0. So Zi1 is 50 parallel minus J50 cot beta L, which is equal to Z0. So it has to be 50. When this will become equal to 50? Only when this is infinity. Okay. So minus J50 cot beta L has to be infinity. When will that happen? When beta L is equal to m pi. Okay. So for that, length of the transmission line, capital L, will be m pi by beta. So m pi by beta will be 2 pi by lambda. So it can be written as m lambda by 2. Okay. Lambda can be written as v by f. So mv by 2f. So this will be the length of the transmission line for which reflection coefficient is 0. So let us take a look at the graph where the reflection coefficient goes to 0 at 1 gigahertz, 2 gigahertz, 3 gigahertz, etc. Say the first is f is equal to 1 gigahertz. Say if I take that into account, L will be m. So m I can take it as 1, and v, the velocity of the signal in the transmission line, is 2 into 10 power 8. So 2 into 10 power 8 meter per second divided by 2 into f, that is the frequency, 1 gigahertz, 1 into 10 power 9. Okay. So this gives us 1 by 10, which is 0.1 meters. So this will be the minimum length of the transmission line T2 for which the reflection coefficient, the input reflection coefficient at so and so frequencies becomes zero. Yeah. So this is the minimum length is 0.1 meters. 0.1 meters. Now let's move on to the next question. Write whether the following statements are true or false. So the following question says on true or false. All R and X circles pass through gamma R, gamma I is equal to 1, 0. So R circles and X circles pass through 1, 0. Whether it's a true or a false statement. So all of you know that this is the center and all R circles and these are all X circles. Okay. So this is true. Okay. Now question B. Any impedance repeats itself every lambda by 4. So every quarter wavelength, whether the impedance repeats or not. So if you have looked at the video lectures on input impedance, you have understood that every impedance repeats itself every half wavelength. Okay. So this is a false statement. Every impedance repeats itself at every half wavelength. Now the question C is an S is equal to 2 circles. So what is S? S is basically the VSWR. VSWR is equal to 2. That is one circle. Okay, that corresponds to gamma equal to 0.5 or not. That is the question. Say if gamma is 0.5, how do you calculate VSWR? VSWR is 1 plus mod gamma by 1 minus mod gamma, which is 1 plus 0.5 divided by 1 minus 0.5, which will give you 1.5 by 0.5. So this corresponds to S is equal to 3 circle. Okay. This is not S is equal to 2 circle. So again this statement is false. So gamma is equal to 0.5 corresponds to S is equal to 3 circle. Now question D. If gamma is equal to 0, it is a matched transmission line. So that is very easy question. If the reflection coefficient is 0, it is a matched transmission line. It's true. Impedance matching. So last part. Impedance matching using a lambda by 4 line is robust frequency insensitive matching technique. Is it a true statement? So what do you mean by a impedance matching using lambda by 4 line? So you are using a quarter wave transformer, or we call it as a lambda by 4 line. So to match Z1 to say Z2. So if you use a quarter wave transformer or a lambda by 4 transmission line, so this should have an impedance Z0 is equal to root of Z1 into Z2. Okay. So the characteristic impedance of the quarter wave transformer which is to be used for matching should have an impedance root of Z1 into Z2. Okay. And also this should have a length of the transmission line should be lambda by 4. See, lambda, when we say that the length is lambda by 4, there itself it is clear that it is a frequency sensitive matching technique. Okay, once if the wavelength changes, there will be a difference in the length of the transmission line required. So quarter wave transmission using impedance matching using a quarter wave transformer is a frequency sensitive matching technique, which is why it is not a very helpful technique or a robust technique. So this is a false statement. Okay. So now let's move on to the next question. For a lossy transmission line, the characteristic impedance does not depend on. So when I say lossy transmission line, so what is the characteristic impedance equation? R square root of R plus j omega L divided by G plus j omega C. So it depends on R, L, G and C, and also on the omega, that is the angular frequency. So it depends on operating frequency. Yes, that is true. It depends on conductivity of the conductors. It depends on the conductivity of the dielectric. But it does not depend on the load, and it also do not depend on the length of the line. So we have option B and C as answer. Okay, Z0 is not depending on the length of the transmission line or also the load of terminating the line. Okay, say if you have a confusion here, conductivity of the conductors means it is the resistance parameter, and conductivity of the dielectric is the conductance parameter. And operating frequency is clear because omega is basically 2 pi f. Okay, now let's have a look at this question. This is interesting to look at the Smith chart. Say if you have consider the path of matching of a load impedance. So this is the load impedance is here to the center of the Smith chart shown in the figure above. Choose the matching circuit used. So we know that this matching has happened from here to here and then here to here. Okay, so from this load point it has come to the matching point. So it has moved along the constant R circle. Okay, so let me write it down. From ZL, so this is the ZL, normalized load impedance point, move along constant R circle and towards the lower half. Okay, towards the lower half of the Smith chart. So it is clear it should be a series capacitance. Okay, then it's moving up along the constant G circle. So it will be a parallel inductor. Okay, so series capacitance and parallel inductor. So from the load, okay, from the load, first you have a series capacitance and then you have a parallel inductor. Okay, so this is the right option, option D. So once you know the matching circuit, you know how the matching the LC matching circuit helps in the matching. Now let's look at this one more question. The length of the transmission line is 500 meter. Okay, 500 meter lossless transmission line of characteristic impedance 100 ohm. So Z0 is 100 ohm, terminated by a load impedance of 50 minus 15J, and the lambda is 150 meters. How many voltage maxima exist on the line? Say, let me write one more point, that is 500 meter is the length of the transmission line. Okay, so now all of us know the standing waves. So the distance between adjacent maximas will be lambda by 2. Okay, so consecutive Vmax is separated by lambda by 2. Now you know that the lambda is 150. So what will be lambda by 2 will be 75 meters. Okay, and the total length of the transmission line is 500. So in that, how many maximas will be there? So you will have totally 7 maximas. Okay, if you calculate, you will get this as 7. So here we end the session. So this was the tutorial session for week 3. This was tutorial session 3, and the content, the sample problems were based on the content of week 3 and week 4. Thank you.